Welcome back. I'm Michelle Sander, and today we are going to be talking about some of the basics of nuclear chemistry, including a form of notation you can use to keep track of your nuclear reactions. So our learning target for today is to be able to write balanced nuclear reactions using something called the nuclide notation. So when we use the nuclide notation, we are very quickly and easily showing the reader the isotope of the element that we're talking about, the element in question. So let's take a look at my picture example up here. Here are some different isotopes of hydrogen. All of them have one proton because, of course, every element of hydrogen has only one proton. That's its unique characteristic that makes it what it is. One proton. And they have differing numbers of neutrons, which is what makes them isotopes. This first protium isotope of hydrogen, has just the proton and electron, no neutrons in its nucleus. Deuterium, on the other hand, has one proton and one neutron, hydrogen 1, and hydrogen 2, tritium, has one proton, because all hydrogens do, and two neutrons. So there's a way that we can write this in a common notation that's easy and quick and takes care of these isotopes problem for us. So for example, carbon-12 is an atom of carbon that has 6 protons and 6 neutrons. So the way we write it in nuclide notation is to write a capital C, that stands for carbon, put its atomic number 6 down here in the lower subscript ahead of the atomic symbol. And then above, we're going to write the mass number. That is to say, the sum of the number of protons and neutrons. 6 plus 6 is 12. And now you know why it has the name carbon-12. Carbon-13, on the other hand, while still has the symbol carbon and it still has 6 protons, but up here in the superscript, we're going to write the mass number, which is the sum of the protons and the neutrons at 13. So a little note to yourself here, remember that this is the mass number. Which is another way of saying number of protons plus the number of neutrons. Let's take a look at a generic formula that might help us make sense of the nuclide notation. So whenever you're writing a nuclide, you want to, let's say you have any chemical symbol, we'll call it X, and this is the symbol from the periodic table. That can be found on your handy dandy periodic table. A chemist's best friend. The second number that's important is your atomic number. So we are calling Z the atomic number. It's another way of writing the number of protons, which, as you know, literally defines what kind of atom we're talking about. And this is to say the number of protons, Z. Up here, you have the mass number, which we will call A. A is our mass number. And it's simply an accounting of how many subatomic particles we have in the nucleus, how many protons plus neutrons are in the nucleus. So there's kind of a generic explanation of what nuclide notation is. In nuclear chemistry, an atom is referred to as a nuclide and is identified by its number of protons and its mass number. So in other words, the nuclides are always written in this format. Let's practice some of them. Take a second and see if you can write the following hydrogen 2 and uranium 239 using nuclide notation. If I look at my periodic table and I try to find hydrogen, here it is up at the top, hydrogen. I see it has an atomic number of 1, so I'll make a note of that. Come on back here and write out my chemical symbol hydrogen and its atomic number 1. Now this number here is our mass number, so it's just going to live right up here on the superscript before the element. Now uranium, on the other hand, uranium 239, let's find uranium. Where is it? All the way down here at the bottom. Uranium has an atomic number of 92, and its chemical symbol is U. So I'll write U, the atomic number 92. And this 239 is our mass number. That's going to go right up top. Now, let's say you wanted to use nuclide notation and write about it in a paragraph. You need to be able to write this out in like in English, in regular English. So how would you write the following nuclide in everyday language? I'll give it to you here, and then you could pause the video, look at the periodic table, and see if you can find the names of these elements. You'll follow them with a dash like we did over here, and then put their mass number right after their symbol. So jumping over to my periodic table, I'm going to find potassium. Here it is. Potassium has an atomic number of 19. I'll remember that and bring it back here. There it is, potassium 19. Give it a dash. And then just like I did with hydrogen over here, I'm going to take that mass number, and this isotope is referred to in English as potassium 40. Looking at this element right here, if I were to look on my periodic table, I find Fe, there it is, iron. Come on back to my problem, and this isotope is known as iron 56. And it's that simple. So that's how you want to write these isotopes when you're writing in paragraph form, writing in English, and when you're working nuclear problems and balancing nuclear reactions, you'll use this nuclide notation here. So be able to interchange between those two different techniques as you see fit. So let's talk a little bit about what a nuclear reaction is. A nuclear reaction is pretty simple. It's just a reaction that changes the nucleus of an atom somehow. So it's a reaction that affects the number of protons or the number of neutrons that your element has. Some nuclei are stable and some are not. And these unstable nuclei are the ones that tend to undergo nuclear reactions. And that instability can either be induced, like our example here, a neutron being fired at a particle of uranium. It creates an unstable nucleus that then splits into two smaller elements while releasing a tremendous amount of energy. Nuclear reactions. Or it could be a spontaneous decay. So these unstable nuclei undergo nuclear reactions. And here's my abbreviation for reactions. Whenever this happens, whenever a nuclear reaction takes place, it releases a tremendous amount of energy. And in some instances, we're able to use that energy, like in the instance of a nuclear power plant. Like chemical reactions, nuclear reactions can be written in a formula, and they can be balanced and solved. So let's try doing that today. In a balanced nuclear reaction, the total number of the atomic numbers and the total number of the mass numbers must be equal on both sides of the equation. And the reason for that is no matter what kind of reaction we have, we're going to start with a certain number of protons. We should end with that certain number of protons. No, none of the subatomic particles are going to cease to exist or, be created or destroyed in this process. So we need to make sure we count them all up and make sure we take a careful accounting of each. So let's take a look at an example of a balanced nuclear reaction. I have beryllium-9. It has 4 protons in its nucleus. It has a mass number of 9. If it undergoes a reaction with helium-4, my result is an atom of carbon-12 and 1 leftover neutron. So here's a handy little piece of information. If you ever wish to have a neutron by itself, alone, not inside a nucleus, you can write it this way. And this makes sense because remember, the atomic number is the number of protons. There are no protons in a neutron. And the top number is your mass number. That's the total number of neutrons plus protons. So 0 protons plus 1 neutron is 1, and you'll have that go up there. So what I mean by balanced is if you look at these numbers, 9, 4, 12, and 1, what we expect to see is that the sums on each side are the same. So 9 plus 4 is 13. 12 plus 1 is 13. That checks out. Let's take a look at the bottom numbers, the atomic numbers, the number of protons. 4, 2, 6, and 0. 4 plus 2 is 6. 6 plus 0 is 6. And so this is said to be a balanced reaction. This is an example of a balanced nuclear reaction. But notice something. When the atomic number changes, like it did in this example, the identity of the element changed. When I took beryllium, 4 protons, and bombarded it with helium, 2 protons, I ended up with an element that was 6 protons. This is a completely different element than I started with. So when the atomic number changes, the identity of the atom changes. Only protons can give the identity of the atom in question. So this is interesting. This is a new feature, and this has a title called transmutation. See if I can do that a little neater. Transmutation, when a nucleus undergoes a reaction that changes its identity or changes the composition of the nucleus. Transmutation, a change in the identity of a nucleus as a result of a change in the number of its protons. And like I was saying earlier, to indicate a single neutron all by itself in a nuclear reaction, we use the following nuclide notation, lowercase n for the neutron, 0 protons in a neutron, and 1 neutron plus 0 protons equals 1, your mass number up top. So now we're going to use these neutrons all on their own to try to balance some chemical reactions. And this is a skill that you'll want to learn how to do on your own. So let's practice. Use the correct number of neutrons to balance. And you can place a single or multiple neutrons on either the products or the reactant side in order to balance them. So let me give you an example. Try this one. Bismuth 209 plus helium 4 reacts and you're left with astatine 212. So my question to you is, what goes here? What goes here? I'll give you another example to practice. And one more. See if you can fill in the blanks. Pause the video, take a moment, take a look at your periodic table, add up your mass numbers on either side, add up your protons on either side, and fill in the blanks with how many neutrons you think you would need to solve these problems. Oops. So let's start by doing some math. On this side of the equation, I have 83 plus 2. 83 plus 2 is 85. On this side of the equation, I have 85. That checks out, so I don't need any number here. I don't need any extra protons to balance this equation. 209 plus 4, 213 on this side, 212 on this side, so I need one more to get to 213. I'm going to need one more. And what do you call it when you have just one in the mass number, no protons and one neutron? That's just a plain old neutron. Same thing here. We've got 40 on this side, 41, 40 plus 1 on this side. So it looks like I'm going to need one more neutron over here. And I'll check my protons just to make sure. 19 plus 1 is 20. Over here, I already have 20, so I'm good to go. I'll put a 0 there. And so this little neutron, just one neutron, is all it'll take to balance this equation. All right, the last one's a little bit tricky. We've got 92 plus 1, plus 1 is 93. All right, that works out, so I don't need anything here. 239 plus 1 is equal to 240. And on this side, I have 238. So how am I going to get 2 more neutrons to balance this out? I can't have 2 neutrons together, but what if I just had 2 neutrons on their own? So the difference between writing this and writing this can be visualized in this way. Here I have a neutron and a separate neutron. And they're just 2 of them. That's just the count. Here, I'm talking about 2 neutrons occupying a nucleus together, which doesn't happen. So we wouldn't write it this way. We would put this coefficient out in front in order to identify that we're talking about 2 neutrons on their own, individual neutrons. So now let's practice balancing some nuclear reactions that don't include neutrons. You're going to have to try to figure out what element goes in each of these spaces in order to complete and balance the reaction. Remember, this reaction arrow means that everything on this side and everything total on this side need to observe the conservation of mass. That is to say, we need to have the same number of protons on the reactant side as we do on the product side, and the same number of neutrons as well. Same thing on this one, so make sure everything on this side corresponds to the same number of protons and neutrons total as on this side. You're definitely going to need your periodic table for this one, so pause and see if you can do it on your own. The first thing I would do is determine what my mass number is on each side. On this side, I see that there's 212 total mass number. On this side, I have 4 plus something. So what is it that when added to 4 will equal 212? That's the question, and that's going to go right here. So 212 minus 4 is 208. So the number 208 is just going to go right here in my superscript. That's the total number of protons plus neutrons that'll be on this element right here. Let's take a look at the bottom. So I need somehow to get 84 total protons on this side of the equation. I have 2 to start with, so blank something plus 2 needs to add up to 84. And the only number that'll work there is 82. So I'm going to have an element with 82 protons and enough neutrons to get to 208. My last piece of information that I need is, what is the chemical symbol? Luckily, 82 is the atomic number. It's the number of protons. So I'll look over to my periodic table. I'll scan until I find number 82. Oh, there it is. Lead. Lead, which has the chemical symbol Pb, comes from the Latin for plumbum, which was the Latin word for waterworks. They used to make all of their pipes out of lead. So we would say in English, this reaction says polonium-212 reacts to form, that's another way of saying this reaction arrow, helium-4 and lead-208. And we've balanced the nuclear reaction. Let's take a look at the next one. Here, I've got rhenium 187 plus is going to react with something. They'll react to form rhenium 188 and one particle of hydrogen. So let's take a count. 75 plus 1 equals 76 protons. Over here on this side, I already have 75, so I think I just need one more proton to balance it out. Up on the top here, I've got 188 plus 1, so 188 plus 1 is 189. So on this side, I have 187 already. I need to get to 189, so I'll put a 2 here. So now I have to find a chemical symbol, an element that has one proton. So I look at my periodic table, and fortunately, there's only one element in the universe that has one proton, and that's hydrogen. So I'll come on back and just write that chemical symbol H to balance the reaction. So this doesn't look that different, except if you notice, this rhenium 187 seems to have gained one of the neutrons from this hydrogen. So 187 went to 188, it got a little bit bigger, the hydrogen got a little bit smaller, and it lost one of its neutrons in the process. But overall, we have the same number of neutrons and the same number of protons as we started with. For our final example, we've got beryllium 9 and helium 4. They will undergo a reaction to form something, some mysterious element plus a neutron. So over on this side, I've got 4 plus 2 equals 6 protons. I have 0 protons on the reaction side, so I'll put a 6 here. 0 plus 6 equals 6. On the mass number, I have 9 plus 4 for a total of 13. I already have 1, so I'll put a 12 here because 12 plus 1 equals 13. So what element is going to go in this? Again, I just consult my periodic table. I look for the only element in the universe that contains 6 protons, my dear friend carbon. And we'll write a big C there for carbon. And that's how you balance a nuclear reaction. It's that easy. You're just counting, searching on your periodic table for the corresponding symbol with that atomic number, and you plug it in the answers. Double check your math just by adding up the superscripts and subscripts on each side and making sure they're equivalent to one another. All right, next time we meet, we're going to practice some more of this in class. I hope you guys have a great weekend.